Good morning, student. Today I'm going to discuss about nuclear rotation and Nielsen unified model for nuclear rotational and other energies. In the previous class, we have discussed about nuclear vibrations of the deformed nucleus. Now, in discussing about nuclear rotation, let us consider the kinetic energy of the nucleus, which can be written in this form: kinetic energy T equals to half V beta square plus beta dot square plus beta square gamma dot square plus half summation over K I K omega K square. Now this part is vibrational and this part is rotational. We're going to discuss this part today. Now H rotational would be half summation over K I K omega K square. Now if we write it in terms of angular momentum, so this will be summation over K L K square by IK. Sorry, IK. Now we know, according to quantum mechanics, angular momentum is quantized. So this form can be written as half summation over K H car square JK by IK, where JK is the angular momentum quantum number corresponding to the angular momentum operator Lk. So if we sum up these terms, summation over K equals K runs from 1 to 3, then this will be H car square by 2 I J1 square plus J2 square plus H car square by 2I 3 J3 square. H car square by this thing, where we have taken I1 equals to I2 equals to I due to symmetry, considering symmetry. Considering symmetry of the problem, I1, I2 equals to I, symmetry of the problem, and I3 is different from I1 and I2. Now, if total angular momentum J equals to J1 plus J2 plus J3, then this can be written as H car square by twice I, J square minus J3 square plus H car square by twice I3 J3 square. Now you know eigenvalue of J square is to J into J plus 1, and that of J3 equals to K. J square and J3 eigenvalue is K. If we replace this thing here and do a little bit of calculation, then energy E rotational comes out to be 8 cos square by 2I into J plus 1 plus H cos square by 2 1 by I minus 1 by I3 into K square. Now I and I3 are close, so this number will be small. And K is small. This is also very small. So this term can be negated in comparison to this term. So finally, we get the expression for energy rotational. This is very simple. You know, this expression is for a single body, for a single body. So this is the expression. Now, as in case of vibrational motion, in rotational motion also, as there is a axis of symmetry, and you know the symmetry axis is along Z dash axis, OZ dash axis, that means body set of axis, and wave function is symmetric about the reflection about the plane perpendicular to it. So this can be it can be shown that the permissible angular momentum have values 0, 2, 4, 6, 8, dot, dot, dot. And the parities are even, you know, parities would be even. The quantum mechanical consideration leads us to this. Now, what is the experimental data that are there? For many even nuclei in the strongly deformed region, we are considering even nuclei, so that the shape is nearly spherical. Then for many nuclei, for example, A equal to 24, and from A equals to 145 to for A equals to 24, 145 less than 180, and A greater than 200. For this type of nuclear, such level situation has been observed. That means 0 plus, then next excited is 2 plus, then next excited is 4 plus, and then 6 plus, and so on. If we will not getting the odd numbers, that means 1 plus, 1 minus, or 3 minus, we are not getting. For example, if we take a nucleus HF 180, for HF 180, the experimental and theoretical values are like this. This is 0 level. First excited state is 2 plus. Then this is 93. So this would be 4 plus 307. All are in keV. All are in keV. Then 6 plus. This is 637. Then 8 plus. This is 1079. This is experimental value. Experimental. Now, what are the theoretical values? If we write this equation, the equation was energy ER equals to h cos square by twice I, sorry, J into J plus 1. This is the equation. We have to match this equation because we don't know what is the value of h car, what is the value of I. Moment of inertia of the nucleus cannot be determined. So you have to feed this thing. If we feed this thing with the experimental value, that means for 2, j equals to 2 means for 2 plus h car square, I'm sorry, h car square by h car square by twice I into 6. If we put the value of j equals to 2, 6, then this would be 3h car square by I. This is equals to 93 kV, from which we can get h car square by twice I would be equals to 93 by 6, right? This will be 15.5, I guess, kV. So now we know this value, right? And for E4 by E2, E4 by E2, how much it will be? 10 by 3. So if we multiply this by 10 by 3, then it will be 30310. I'm sorry, this is 93. These two must be matched, and this will be 310 kV. And the next E6 by E2 would be how much? E6 by E2 would be 7. So this will be 7 times 651 kV. It will be 651 kV, somewhat upper than this. And E8 by E2 would be similarly 12. So this would be 1160 kV. So you see the value, experimental value, and the predicted value, theoretical value that we are getting from our analysis are close, though there is a systematic difference. As we go upwards, difference is larger. So we can, but still it is very small. So we can say that our understanding or our as we have assumed the rotational state is verified by the experimental fact. Now, why this is different from, why there is a minute difference, why there is a little difference and systematic difference, this is thought to be due to the change in value of I, that is moment of inertia. Now, why it will change? Because we know for a nucleus rotation, for rotation or vibration, not the whole part is involved, only a fraction of it is involved. That is, when nucleus is rotating, the rotation is not uniform. There is gradual rotation, means there may be rotation outside, but inside may not rotate. So the moment of inertia for higher energies may be different. In that case, for higher energies, the gradient may be different. That means the outer region is rotating faster than the inner region. That gradual rotational or this type of rotation is also observed in many other large objects which are not solid, and nucleus cannot be taken as solid object. So this explain the rotational motion of the nucleus. Next we move on to the topic Wilson model. Now it is a very complicated model. But we are trying to, I am trying to present it very simply so that you can grasp it. Supposing that you have gone through the study material that I have given. What Nielsen did, actually Nielsen and Newton, not the Sir Isaac Newton, but Newton in 1960 and Nielsen. What they have done, they have solved the single particle wave function wave equation numerical, because exact form of the interaction is not known. So they solved it numerically with different deformation parameter. And the result that they present were also in graphical. Now what they have done, let us go deep into it. What Nielsen has assumed is that angular frequency in the z direction is different from the other two direction, xy direction. So let omega z equals to omega 0 function of delta deformation parameter 1 minus 4 by 3 delta to the power half, and omega x equals to omega y. These are perpendicular. This is equals to omega 0. That means perpendicular to omega z. Omega 0, this function of delta 1 my plus 2 by 3 delta to the power half. He has assumed the angular frequencies in 3 different directions of this form, where delta is the deformation parameter. Now if omega 0 bar represents the deformation free parameter, then we can say that omega x, omega y, omega z equals to omega 0 bar q. Now if we substitute this thing, omega 0 x, omega 0 y, omega 0 z, omega 0 z, omega 0 z, this thing, then at once we will get omega 0 cube delta function of delta into 1 minus 4 by 3 delta to the power half 1 plus 2 by 3 delta equals to omega 0 bar q. After a little bit of calculation, we will see, we'll do, I guess you will do the calculation in your own hand, it will be far better. So just leave 2 or 3 steps and write the final result. Omega 0 equals to delta can be written as omega 0 1 minus 16 by 27 delta square delta naught plus 9 by 4. 9 by 4. From which we can write omega 0 minus omega 0 bar will be equal to minus omega 0 bar 16 by 27 delta square delta plus 9 by 4. So this is the difference from the angular frequency omega 0 to the mean angular frequency omega 0 bar. Now Hamiltonian can be written as H kinetic energy term P square by twice M plus potential energy term half M omega x square into x square plus y square plus omega z square into z square plus two additional terms c into due to spin orbit coupling another term dl square. This is due to spin orbit coupling and this is due to centrifugal acceleration. Now these two terms are additional terms which we have to take into account for the rotational motion. For lower excitation levels, we first approximation that we are doing is taking this term to be 0. And the C is the coefficient. C is taken of this form. C equals to K, a constant, into twice H cut omega 0. Then delta E, this can be written as P square by twice M plus half M omega 0 square R square 1 minus 8 by 3 root over pi by 5 y 20 delta plus CLS term. CLS means twice A H cut omega 0 L dot of S. If we calculate all these terms, y20 is the spherical harmonics, then this comes out to be delta E energy, change in energy comes out to be means change in energy means energy difference in energy between the deformed level and the original level. This also A is a constant into delta deformation parameter 3jz square minus j into j plus 1. Second, for j greater than half, and this expression would be 0 for j equals to half. If j is greater than half, then this is the expression, and this energy difference in energy would be 0 if j equal to half. For example, Let us take j equals to, let j equals to 3 by 2, right? Then delta E would be A delta 3jz square minus 15 by 4. So this will be equals to 3A delta for jz equals to 3 by 2. And this would be equals to minus 3A delta for jz equals to half. So depending value of jz, the difference of energy is changing. You see, for jz equal to 3 by 2, this is 3A delta, that means change is positive, and for jz equal to half, minus 3A by delta, the change is negative. And similarly for the state 5 by j equal to 5 by 2, you can calculate it. Now, eigenstate of H is determined by principal quantum number, and the principal quantum number n equals to n1 plus, rather, I may write it nx plus ny plus nz, nx plus ny plus nz, and orbital quantum number L, and z component of angular momentum lambda, and z component of spin. Now, in the graph, I am drawing it a little bit to the graph for Nielsen model. What it has taken k equals to the to 0.08 and deformation parameter delta. You know, for s equal to, for s level, because j equal to half, so this state will not be splitted, but the state p3 by 2, this state will split. P half, this term will not split. Next term d5 by 2, this will split into 3 terms. Five by 2, 3 by 2. This is for positive delta. For negative delta, the same thing. Will be obtained. These are the cells, these are 0, 2, 8, and d5 by 2, upper level will be s half, this will not be splitted. Then another level will be d3 by 2, this will be splitted again. With the values of k, this splitting is there. The numbers, the quantum numbers, we call this state to be half. That means it's z component of angular momentum, jz value actually. Half parity is -1, 3 by 2, 3 by 2, parity minus, and its other quantum number 110, 101. This denotes principal quantum number m. capital N. This denotes Z component NZ, and this denotes lambda, the Z component of LZ, orbital quantum number. Now, Nielsen model is here, it is drawn for n less than 20. The state is labeled by J, the parity and the three parameters as n, n3 and lambda. Lambda is the Z component of L. Now, using Nielsen wave function, it is possible to predict many important properties of ODE nuclei as a function of deformation, such as magnetic and electric quadrupole moments can be explained using Nielsen model. In fact, Nielsen model is a very complicated model, and if you go through the full chart, the table of Nielsen graphs, there are many things which cannot be explained with plain logic, but somewhat it will explain many things, like, as I have said, like that of magnetic moment and electric quadrupole moment. So this is all about our cell model. If I can recapitulate the cell model, then first we have considered about the cell model without spin orbit coupling in the previous semester, where we have seen that in order to explain the magic numbers, the cell structure has to be considered. Now, considering the simple cell structure, it was not possible to explain magic numbers beyond 2 or 3 numbers. And to explain them, spin orbit coupling was introduced. Introducing spin orbit coupling, the magic numbers could be explained. Moreover, spin and parity of many nucleus could be explained. But what about the odd nuclei? We have not discussed in the previous semester. From this semester, we are considering the cell model in which even odd nuclei, magnetic moment and spin and parity of odd nuclei is considered. And we have seen that there Nordheim's rule is applicable, and using Nordheim's rule, we can predict magnetic moment, spin of many nuclei. Though the agreement with the experimental values is not so satisfactory, but it can explain little bit. Other models like collective models are also discussed, in which the collective motion of the loose nucleon and the rest of the nucleons have been considered. And due to the loose motion of the loose nucleon, the deformation of the nucleus from the spherical shape has also been considered. And we have seen that the large quadrupole moment, experimental very available large quadrupole moments of the many nucleus could be explained using collective model. Then next we have considered the rotational and vibrational energies, and we have compared our theoretical foundation with the experimental finding. In both cases, in case of vibrational motion and in case of rotational motion, experimental data quite matches with our theoretical predictions. And finally, we have considered about Nielsen model, which is a numerical model which has been solved using computer simulation using different deformation parameters and the splitting of different energy levels. And this splitting of energy levels can explain many important properties, explain and predict many important properties of nuclei, such as magnetic moment and electric quadrupole moment. Thank you. Next, in the next, we will discuss to the other part of the problem. We have considered two aspects of nuclear structure. One was about the cell structure, and other was were considering the scattering of nucleons. Now, in scattering of nucleons, we have taken deuterium nucleus, because this is the simplest nucleus that we have in nature. And we'll, in the next class, we'll discuss about scattering of the deuterium. But many greater part of it has been discussed in the previous semester. We'll discuss the next part, that is where we left in the previous semester. We'll start in this semester. Thank you very much.